QIQT conference. So basically, the idea of the tutorials is like it's mainly intended for students who are just starting off and would like to learn more about quantum computing and quantum mechanics in general. And so basically, a lot of them don't have the prior prerequisites for starting off or understanding the research talks which are going on right now. So the idea is to give them a brief introduction to the topic. Okay, so before we start with the serious topics, I would like to give a brief introduction to the to what the different quantum computing and quantum communication, what those things are. And so, okay, so yeah, so the first quantum revolution consisted of these semiconductor electronics, superconductors, lasers, and so on. So basically, these are things which we have right now, which are being used in industry and household all over the world. And all these things are based on the laws of quantum mechanics. They follow the laws of quantum mechanics, and these were the things which we got in the first quantum revolution. And now in the second quantum revolution, so what happened is that in these things so a lot of we did not encode information. For example, semiconductor electronics enabled classical computation, but the information itself was stored classically. So the information was never encoded in quantum states. So in the second quantum revolution, the key idea is to encode information in quantum states. And so if we compare classical and quantum bits, the classical bits is like 0, 1. So at any point of time, a given classical bit is either 0 or 1. But quantum bits have these peculiar properties of, say, superposition. For example, in this state, 0 plus 1 by root 2. Here, we can't say that this quantum bit is in the state 0 or state 1. The closest that we can say is that it's kind of both in 0 and 1 at the same time. So this property of superposition gives parallelism to quantum computation, to quantum bits, which is not present for classical quantum computation or classical bits. And this the other peculiar feature which we have for quantum bits is entanglement. For example, if we have, say, two classical bits, then if we say measure or disturb one of them, the other will not uh, get affected in general. But in entanglement, what happens is that even if the quantum bits are taken or the qubits, as we will call them from now on, if even if they are taken very far away from one another, if we measure the first qubit, and if we get 0, we are assured that if you measure the second qubit, you'll also get 0. So, or vice versa, if you get 1, then you're assured that the other qubit, you will also, if you measure, you will also get 1. So these kinds of like these two properties of quantum bits is what makes them special and different from classical bits, generally speaking. Yeah, and the second quantum revolution is based on the idea of this encoding information in quantum states, and in specifically two-level quantum states or qubits. And in the second quantum revolution, the three main verticals that we have are quantum computing, communications, and sensing. So quantum computing, quantum computing is the idea of using the parallelism, the resources of superposition and entanglement to make certain algorithms faster. Uh, so uh, we can make something run faster in two ways on a computer. So one way is to uh, make the time required for each computational steps small, or reduce the number of computational steps which is necessary. Uh, so make that small. So quantum computing does the latter. Quantum computing reduces the number of steps you need to perform a certain task, as opposed to uh, in reducing the time taken for one uh, iteration, let's say. So, for example, let's say you had a problem which you previously say for if this problem was the size of the problem was n, you would need some order of 2 to the power n steps to solve it. Now you can say solve it in just n, or like in n steps, in order of n steps. So that is the basic idea of quantum computing, and the applications are in a diverse number of areas. So some of the algorithms which quantum computing makes faster is the problem of factoring large numbers, uh, the calculation of discrete Fourier transforms, and so on. And some of the applications are in cybersecurity. So basically, uh, if you look at today's encryption system, some of it is based on the RSA encryption, for example, is based on the fact that classical computers today cannot uh, factorize the uh, the product of two prime numbers efficiently. It cannot do that in a very like in a very short time. And so the entire concept of cryptography, or some forms of cryptography like RSA encryption rest on like these difficulty of the problems. So on the fact that certain problems are very difficult to be solved by quantum computers, sorry, classical computers. But quantum computers, for example, can factor large numbers very easily, and therefore, if you have a like a quantum computer with a sufficient number of qubits, you can actually break RSA encryption very easily. So that's one application in cybersecurity. Uh, the other applications are in computational chemistry, machine learning, finance models, transport optimization, etc. So, for example, in machine learning, oftentimes in certain problems we have to do matrix inversion, and that is something which quantum computers can handle very efficiently. They can do it in a much less number of steps. And another important application is the simulation of different quantum mechanical phenomena. And so this is something which actually Richard Feynman had predicted back in the day. He said that since nature is fundamentally quantum, if you want to simulate nature, the simulator has to be quantum mechanical as well. So a lot of quantum mechanical phenomena we cannot simulate today on a classical computer very in fact some cannot be solved on a classical computer, even if you take a supercomputer, for example. And those things, since for quantum computers the qubits themselves are uh, quantum in nature, it becomes possible to simulate some of those problems which were previously we couldn't solve with the classical computers. And the second vertical was quantum communication. So quantum communication is actually an umbrella term for a large variety of things. So the most commonly used context in which we use the term quantum communications is actually secure communication of classical information, as in we are transmitting some classical information. So basically some email or some PDF document. Hello. Okay. So, so something we are sending through some public channel, and we want that the communication should be secure, that a third party cannot eavesdrop into what we are sending. So, in so classical, and actually that is the domain of encryption and cryptography. But for executing any cryptographic algorithm, we or a lot of cryptographic algorithms, we need to share a common key between the sender and the receiver parties. And uh, currently, one of the ways is something like a Diffie-Hellman algorithm, which is a classical algorithm. And uh, again, so basically, it's not so. Given that quantum computers could exist in the future, uh, one could potentially like the key that we are trying to share between two parties can potentially get compromised, and the communication might not be secure, so much secure after all. But the beauty about securing classical information with by quantum means, in particular this quantum key distribution, this allows for communications which is secured by the law of nature. As in, you cannot, in principle, like if you are receiving a transmission from, say, there are two parties, one is sending some information to the other. If the other party is able to receive the information properly and sees, so he can determine if somebody has tried to extract some information in between, or tried to do something with the information in the channel. So uh, QKD allows for that. And another context in which we use quantum communication is efficient communication of classical information. So let's say you needed 1,000 bits to of classical 1,000 classical bits to send some information across. Now you can do that with 500 quantum bits. So so that is exactly what some protocols like super dense coding does. And the third thing that one can mean by quantum communication is the communication of quantum information itself. So we have a quantum state, and we want to transfer that state from one lab to another without actually moving that qubit around. So that is something which is done by quantum teleportation. And the third thing that we have here is quantum sensing. And what it helps us is to measure various parameters with extremely high precision and across wide dynamical ranges. What that means is that uh, it's not only that it's very precise. Uh, so, for example, we have an NV center sensor which can sense magnetic fields, for example. So uh, the sensor, it can give you very precise values of the magnet. But not only can it give you like the values of very small magnetic fields, it can operate up to very large magnetic. So across a very wide range of magnetic fields, it can give you very precise measurements. So uh, and not only magnetic field, temperature, electric field, mechanical stress, these are some of the things that can be measured very accurately. And for example, by NV center sensor. And so we also have cold atom sensors, which can give you the gravity, position, time. These things they can measure very accurately. So yeah, so that's quantum sensing. Now, I'd like to briefly mention some of the experimental platforms for quantum computing. So The first and the most popular and probably the most successful till now is superconducting qubits. And uh, the advantage is that it's on a conventional solid state on a cheap based platform, which is very already very well developed thanks to our uh, this electronics semiconductor revolution. And uh, but the main problem with superconducting qubits is that requires very low temperatures and sometimes like always millikelvin order temperatures in order to function. So uh, whenever you are trying to scale the number of qubits, like increasing the number of qubits, then that becomes a bit of an issue because the heat load on the dilution refrigerator, which is keeping it cool, increases, and um, and you need to uh, make better cryogenic systems. Say if you want a million qubits, or so then the current level of cryogenics will not really help you. Uh, and okay, and it's worth mentioning that the lines that you see here on the chip are basically these are microwave transmission lines, and they actually provide the control signals, the microwave control pulses to the qubit and performs the various gates on. Uh, and the next most popular platform for quantum computing is probably the trap-time quantum computers. So here there are two electrodes. Sorry, there are two electrodes, and the a linear chain of atoms is trapped between them, and using lasers, they are manipulated. So and these also require very low temperatures, but the cooling but on whereas in the superconducting quantum computer we actually had to cool the hardware down using a dilution refrigerator down to millikelvin. Here lasers do the job for you a lot of the times. So basically lasers cool the atoms down to millikelvin temperatures. You don't need necessarily a dilution refrigerator in order to do this. And another very popular and in recent times it's been giving very good results is photonic quantum computers. And so here the idea is to use the quantum states of light in order to do in order to do computing. And the advantage is that light and one of the problems with say traptan or superconducting qubits or any qubit is decoherence, is that it, it interacts with the environment very easily, and it loses its quantum state very fast. And in for optical qubits, that restriction is not there so much. So basically, these qubits do not interact in general with the environment so strongly as strongly as the other solid state platforms would do, and so they are more robust to environmental noise. And but again, one of the difficulties here is that since they do not interact with the environment, they do not interact with each other also so much. So it's difficult to entangle, say, two photonic qubits, more difficult to entangle two photonic qubits compared to entangling two superconducting qubits, for example. So here you can see some ring resonators in on the chip. So basically, what they do is from the quantum light sources, they take the light and they squeeze it. They generate some states of light called squeezed light, and then there are some. phase shifters and beam splitters in between, which basically manipulate the quantum states of the light. And then finally, the readout happens at these single photon detectors. And yeah, finally, I'd like to discuss some of the experimental platforms which are being developed at either Kolkata. And so this is a pulsed electron spin resonance platform is one of them. So here you apply a magnetic field, and because of the Siemens splitting, so you have a paramagnetic system, spin half system, and because of the Siemens splitting, it gets split into two. The degeneracy is lifted, and two energy levels are formed, and we use this system as a qubit. Um, so this is the setup in the left corner. You can see the setup which we have used for doing this, and the free induction decay signals and the Rabi oscillation signals are shown. So as of now, this is the status that we uh, do not have a very good Rabi oscillation. So uh, that is something we are working on right now. And we are also working on nitrogen vacancy centers in diamond. So it's basically a defect center in diamond. So diamond is made up of carbon atoms. So the black balls that you see here are carbon atoms, and one of the carbon atoms is substituted by nitrogen, and adjacent to it, you have a vacancy. Now, this defect center takes a negative charge from the lattice, and it becomes a negatively charged nitrogen vacancy center, and that is a spin one system. And so you can see in the energy levels that in the ground state of the triplet, there is some ms0, ms plus minus 1. So we take, say, ms0 and ms plus 1, or ms0 and ms minus 1, and use that as q. And this is the ODMR spectrum, optically detected magnetic resonance spectrum of the system. So one great thing about the system is that the optic initialization and readout happens optically, whereas the manipulation, that is the quantum gates, happen with the help of microwaves. So uh, yeah, so basically the green laser initializes everything to ms equal to 0, and the intensity and when it decays, some red photoluminescence is emitted, and the intensity of the red PL, or in case of a single NV center, the whether a red photon is emitted or not, that tells us that basically reads out the quantum state. So if a red photon is emitted, it goes in ms equal to 0. If it is not emitted, then it is ms plus 1 or minus 1. Like okay. So finally, I'd like to comment that this quantum computing or communications or sensing, like any of these verticals for the second quantum revolution. Uh, so this is a very interdisciplinary field, like if you consider any of them, and it involves quantum physics, of course, and with mathematics. So quantum physics is based on very abstract mathematics. So of course mathematics comes into the picture, but other than that, for algorithm development also, mathematics is very important. And then computer science. Computer science is needed in both the context of theory and experiments of the field. So, say algorithm development is there, and when you are running an experiment, then how we can map the like problem at hand, the classical problem that we want to solve, to the quantum computer, or how to interpret the results coming out of the quantum is something which falls under the paradigm of computer science. And because you need to understand that, for example, in classical computers, it's the processor. There are so many things which is revolving around the processor that we have, the processor chip. So uh, it's not sufficient to have only the processor. You have to so when we say run some program, it has to be compiled and mapped onto the processor, and then it has to be read out again. So similar thing is true for quantum computation, and uh, it's more non-trivial than it is in the case of classical computing. Um, and of course, and surprisingly, there's this thing of philosophy also, and because uh, the uh, uh, the different phenomena that I had been referring to, for example, superposition, entanglement, uh, as we shall see later on, that not all of them are very um, well, they're well understood, but uh, they lead to classical paradox. So, from a classical point of view, they are not always so acceptable. So, and some of these uh, Bell non-locality and other things are actually they have a lot of philosophical component also associated with it. So yeah, that's one. And of course, for doing the experiments, you need electrical and electronics engineering, optics, and a lot of cryogenics is involved in general. Um, okay, and uh, the tutorial. So this was a brief introduction. Like I'm afraid I might have confused you a little bit in this introduction, because I might have told a lot of words which you don't know or something, but don't worry. We will go very step by step. So we will start with the Stern-Gerlach experiment, and with the help of this experiment, we will try to see okay, why quantum mechanics is needed in the first place, why classical mechanics fails, and then we will study the postulates of quantum mechanics, which are basically the uh, ground rules which we accept, and from there we can see that the experimental results are getting validated. So using the postulates, we will explain the Stern-Gerlach experiment, and then we will look at the density matrix formalism, mixed states, and one of the most important topics which will probably be covered is the block sphere, because you would represent a qubit on uh, a single qubit. If you have, then you will represent it on a block sphere, and we will learn how to map the density matrix to the block sphere, and then entanglement and decoherence. So uh, entanglement is useful when two qubits get entangled, but systems also get entangled with the environment, and that leads to decoherence. We will learn that, and we will then study some quantum algorithms, some common quantum algorithms like Gauss-Schwarzer, quantum Fourier transform, Shor's factoring algorithm, and and then we would go to Bell non-locality serial sense bound. Um, and quantum communication. So the last two topics will probably be covered by a colleague of mine, Shukmit Mukherjee. And okay, so that's it for the in the presentation part. Now I would switch over to um, my notes and get started with the Stern-Gerlach experiment. But before I do that, I would uh, stop and ask if there are any questions or queries, confusions.
Hey, this is Dhaval here. Thanks for the talk. I have a question about quantum sensing. You mentioned about
Yes.
different ways um,
Mm-hmm.
in which the quantum computers or quantum chip can be created or entanglement can be created. Which of those ones are suitable for quantum sensing?
Oh, okay, okay. So nitrogen vacancy centers in diamond is something which is a very good quantum sensor. As in, it can measure a lot of things like electric field, magnetic field, temperature, um, and also mechanical stress. Nitrogen vacancy centers is one platform which is very good for sensing, but don't uh, but that doesn't mean that it is not useful for computing as well. It is also, you can do computing with nitrogen vacancy centers. And another thing is the cold atoms. Cold atoms can are very good sensors for gravity, for example. So yeah, so does that answer your question?
It does. Thanks. Thank you.
Okay, okay, okay. Anything else?
Hey, hi, this is Ajay. Ajay, uh, are we going to cover a chemistry sort of application in this course, or can you
No,
please just
no.
touch on that?
Chemistry application.
Uh-huh. Means
Mm,
especially VQA
okay.
part and the hydrogen molecule, ground state,
Oh,
and all those things. So, are we just touching on that topic, or could you please just brief us
no,
on that?
no.
Will be great.
Okay. Actually, hydrogen atom or those things like that would be typically the content of say like typical quantum mechanics course. So
Okay,
the
okay.
idea is not to teach you just quantum mechanics, but
Uh-huh.
to teach you quantum mechanics in the concept of in the context of quantum information processing or quantum computation, for example.
Oh, okay, okay.
So basically, learning hydrogen atom would not really help you understand qubits. Well, of course,
Yeah, that's true.
yeah,
Correct.
yeah. So we will be restricting ourselves to this only, and
Mhm.
yeah, okay. So if you want to learn about hydrogen atoms, I think yeah, there are a lot of great materials and textbooks which I can refer you to, of course.
Yeah,
So okay.
yeah. Thank you. Thanks a lot.
Uh, uh, okay. Any other questions? Okay, if not, we will start with our first topic, which is the Stern-Gerlach experiment. Just give me a minute. I'll just have some water and I'll be back.
Hello. Hello. Hello.
Hello.
Hello.
Yeah.
There is a question from Parthagos. So,
Huh.
would you like to answer that question or would you like to answer that later?
No, no. Please tell me your question.
Okay. What makes quantum sensors more
Mhm.
precise than optical ones?
That is a very good question, Mr. Nandi. So, so quantum sensors use this phenomena of superposition. So superposition and entangle. So that's what makes them very sensitive. And yeah, so in order to really do a rigorous analysis of why a particular sensor is being more sensitive for a particular measurement, that is a that would be a more involved answer. But just to give you a like um, sense of what is happening is that uh, coherent superposition and entanglement is being used. Now, yeah, you can say that there are some instances where uh, we are not really using. superposition or entanglement, but we still call that a quantum sensor. But yeah, that is an exception. So in most of the scenario, you there are in real life as of today, there are very few sensors which actually utilize entanglement, but almost all of them utilize superposition. Is that okay?
Yeah, there are no questions. You can move ahead.
Okay. Okay. All right. So okay. So the apparatus for this experiment. So I have simplified it a lot for you, so that there is no confusion. So there's okay. So there's an oven from which we are having some silver atoms which are coming out at a very high velocity, and then we are somehow collimating the silver atom beam, and it is passed through the pole pieces of a mat. But these are a bit weird looking pole pieces, so I'll come to that. Let me just draw. Yeah, so in general, if you look at the pole pieces of an electromagnet, they are generally of the same shape. And what that does is it ensures that the magnetic field is uniform or homogeneous in this space, in the space between the pole pieces. But here we have electromagnets where one pole piece is very sharp like this and one is broad. So as a result of this, what happens is that the magnetic field, uh, like they would look something like this, the field lines, and the magnetic field would be highly inhomogeneous. And the inhomogeneity, so let's say this is the Z direction, and hmm, so the inhomogeneity will be along the Z direction. As in, if you look at del pz del z, for example, that would be non-zero. And uh, and then we have finally here we have a screen. Okay, so what the screen does is that when the silver atom goes and hits one part of the screen, it detects that. Okay, so basically the screen detects an intensity distribution, if you like as in key or number distribution. Okay, in this spot, how many atoms are hitting? In this spot, how many atoms are hitting? Like that. Now, suppose there's some silver atom which is passing through here. So the question is, how much force would it feel? Um, or more specifically, since the inhomogeneity of the magnetic field is in the z direction, let's ask how much force it would feel in the z direction. So if we write that, it would be nothing but derivative of the potential energy with respect to z, because the force vector is something like this. It's the gradient of the potential energy. Okay. Now, uh, so uh, uh, in the so silver atom, let's before we delve further into what the force will be, let's look at the electronic structure of the silver atom. So the silver atom has this electronic structure. So here you can see that there is a 5s1, which means that there is an unpaired electron in an s orbital. S orbital, for the s orbital, you know that the uh, L is zero. That is the orbital angular momentum is zero. So the only angular momentum will come from the spin. So because electron is a spin half particle, so it would have a spin angular momentum, and because of the spin angular momentum, it would have a magnetic moment. And the potential. So when a magnetic dipole or a magnetic moment is there in a magnetic field, then the potential energy is given by minus mu dot p. So this is hopefully which we know from high school physics. And uh, in our specific case, it would be something like mu z pz mu y dy and mu x px, something like that. Now, uh, since the inhomogeneity of the magnetic field was along only the z direction, so we had del pz del z0. We will also have del px del z0 and del px. Sorry, not yeah, del py del z. I'm sorry. So, in other words, the x and y component of the magnetic field would not be changing along the z direction. Only the z component would be changing along the z direction. So, uh, now if we go back to calculating the fz from here, then it would be something like del z uh, minus mu dot p. So of course this del by del z del bx del z, these go to zero, and what we would be left with is mu z del bz del z. Till now, is it clear? Are there any questions?
No.
Okay. Uh, Fine. Huh. Now, given this, what do we expect to see on the screen? So the silver atoms which are coming out of the oven, so they will have magnetic moments distributed in all kinds of directions. So basically, what I'm trying to say is that coming out of oven, mu vector is random, and mu z is just the z component of the magnetic moment. So mu z, say if the z, it is if mu vector makes an angle theta with uh, the z direction, let's say z roof, then mu z will just be mu cos theta, right? And since the direction of mu vector is random, theta can be anything from 0 to 2 pi. So any value of almost all values of mu z should be present here. So, say from some so suppose we have some value of mu z. So what will change? So if we have a say a positive value of mu z and a large positive value of mu z, then the force acting on the silver atom will be large. So it will be deflected by a large amount. On the other hand, if the mu z is very small, so cos theta, let's say cos theta is such that mu z is almost zero, then it will almost go through un like without it's undeflected. It would go through without any deflection. On the other hand, if it is say mu z is negative, then it should be negative in the deflected in the negative z direction, because the force would be in the negative z direction. So what we expect to see on the screen is that there would be silver atoms all over the screen almost. Now, but what we do see experimentally is that the silver atoms only are concentrated in a spot here and a spot here. So this is something which we did not expect naively from our classical intuition or from just the basic notions of classical mechanics. So one thing, so what this tells us is that mu z actually cannot have all the values from minus mu to plus mu as it was suggested by this relation. So this said k mu z can go from minus mu to plus mu. But we see that it's not like that, and in fact, we get only two values. So mu z, and it turns out that these two values are something like this: gamma e. Sorry, writing over that. Okay. So gamma e h cross by 2 and minus gamma e h cross by 2. So just these two values. So basically corresponding to mu z, these two values, we get two spots, because from the spots we can calculate how much fz was there, and from the fz, and if we know del bz del z how much non-inhomogeneity is there, we can say which point on the screen corresponds to what mu z. So it was calculated that mu z corresponds only to these two values. So mu z can only be plus minus gamma e h cross by only these two values. Uh, okay, so till now, any questions, queries? Okay. So what this tells us is that mu z is uh, quantized. So this is the first situation, or the first point where quantum mechanics kind of barges into the picture in this experiment. Okay, so that is fine. So we will have to set a new set of ground rules. The mu z will only take those two values somehow. Let's say. Uh, Now, let's do one thing. Let's take this apparatus and
Hello.
hello. Yeah.
I have one question.
Sure,
Yeah,
sure. Go ahead.
Here, gamma is what is
Sure. Right. I'm sorry. I forgot to define gamma E. Yeah, gamma E is the gyromagnetic ratio of electron. Uh, so the gyromagnetic ratio is basically the is the ratio of the magnetic moment and angular moment. So basically, if mu z is gamma a h cross by 2, so gamma e is basically mu z by is that I hope I'm correct. Yeah. So uh, from here you can say that the sz basically sz is the spin angular momentum, the z component of the spin angular momentum, and it would be mu z by gamma e. So basically, if mu z is just gamma h cross plus minus gamma h cross by 2, it would be just plus minus h cross by 2. Is that clear?
yes.
Okay. And E because of electron. Okay. So moving ahead, let's say let us represent this whole apparatus by a box. And since the inhomogeneity of the field was in the z axis in this direction, in this case, let's represent it by the box is g z. Now, if we want to represent the whole thing in a simpler fashion, how would we do it? We would just put the box. Hello, is there a question? Okay, so we have the oven here, we have this coming here, and the box has since now we have seen that mu z can have only two values. The box will have two possible outcomes. So basically, what that means is that the atoms can either go here, or it can go to both the places. So here, what we will do is that another thing in regard to this is that so the spin angular momentum Sz component when it is plus h cross by 2, we would denote it by so basically if okay, where shall I write this? Uh, Let me write it here. So if z equal to plus h cross by 2, so it's a spin angular momentum, right? If the spin angular momentum is plus positive, then we will just call it upspin, but in the z direction. And if it is minus h cross by 2, we will call it downspin, but in that z direction. Okay, so basically, if it is plus h cross by 2, then we know that we are having up spins in the z direction coming out from here, and here we will have down spins in the z direction coming out from here. Okay, and similarly, we can define it for other directions also. So, for example, uh, in general, in some arbitrary direction, if we orient the vector, so if instead of z we take the we place the pole pieces along some n roof direction, then it would be up spin in n direction and down spin in n direction, like that. Okay, now what we would try to do is we would try to take combinations of Stern-Gerlach apparatuses in different oriented along different directions. So let's say, so I'll tell you what I mean. So let's say we take the following. So we have this coming out of the oven. We pass it through the Stern-Gerlach along Z roof, and of course there are both up and down spins in this in among the atoms coming out of the oven. So let's say we block the down spins, so the down spins don't go ahead anymore. We take the up spins and we feed it to the input of another Stern-Gerlach apparatus, which is oriented again along the Z direction. Now, what do we expect? So, since we have allowed only the up spins to go through, when we would pass it through another Stern-Gerlach apparatus, which is oriented in the Z direction only. So we would expect that. So basically, what does it mean? We are allowing only the upspin Z atoms. That means all the atoms which are going through here has Sz equal to plus H cross by 2. Now, yeah. So if what that means the Z component of the angular momentum and the spin angular momentum is plus H cross by 2. If we pass that through another Stern-Gerlach apparatus, what do we expect the output here to be? So if any of you have any ideas, you can unmute yourself and so basically, it has only Z plus H cross by 2. So if you pass that, if the source of silver atoms here did not have both plus and minus H cross by 2, had only plus H cross by 2, where would all the atoms go? So basically, here what was there is that here there were some spins oriented along upset. Here some spins were oriented along downset. So those which were oriented along upset went here, and those which oriented along downset went here. Now what I'm doing is I am removing this down Z component. I'm just passing only up Z here. So what should I expect?
The particle moving upwards.
Exactly. So all the particles will move up. In other words, if we look here, then at the output we will only have up Z particles and no down Z particles. So nothing will come out of here. Is that okay?
Yeah.
Okay. Okay. Is that okay with everyone? I don't know. Like uh, many people. Okay. There's quite a few people, I guess. Okay. So if that is okay with everyone, okay. Then we will get to the other case. Is somebody saying something? Okay. Uh, now, instead of passing through, So the first one is still the same. Uh, we are taking the Stern-Gerlach along the z direction only, and then we are taking the silver atoms from the oven, and we are blocking the down z ones as we had done before, allowing the up z ones to go through. And instead of the putting another Stern-Gerlach apparatus oriented along z direction, what we would like to do now is put a Stern-Gerlach apparatus, sorry, oriented along x direction. So now, what is the expectation? What would you expect would come out of this? Now, notice that the only possible outcomes from here are up x or down x, because say when Stern-Gerlach is oriented along n row, then either up n or down n can come out. So which one will come out? Up x will come out, down x will come out, neither will come out, or both will come out. So that's the question. So I'll give you a minute or two to think about it.
Either one is equally probable.
Either one is equally probable. Okay. Why do you say that? Because I would argue otherwise. I would say they are not equally probable, because I have is that plus h cross by 2, right? So if I think of a vector, this is a classical vector, right? So at least for the time being, it's a classical. Like I'm saying from the purview of classical, which means it's a vector which is oriented along the z-axis with length h cross by 2. And what SGX should do is so say this is the okay, drawing skills are not great. So along the z-axis, it is h cross by 2. What SGX should tell you is what is the component of the vector along x, isn't it?
Yeah. So the SGAZ doesn't, in the classical case, it doesn't affect the spin component along the x direction, right?
Yeah, it does not have. So let's say we do not go to quantum mechanics for the time being. In the classical case, what would you expect? Should you say see up x or down x, or both, or neither?
Yeah, I guess it's neither then,
Exactly.
right?
So
Yeah.
yeah, right, right. So it should be neither, because the component of the s vector, because now the s vector is that is that z hat. So basically plus h cross by 2 z hat. Now the component of s vector along x is 0. So neither this or nor this should come out according to theory. So this is according to classical mechanics rather. So this is what we expect according to classical mechanics. But in reality, what we see is something different. What we see is that as he had pointed out before, they are equally probable, in the sense we saw both the spots in the apparatus, like both the up x and both and down x came out of the apparatus. So this is what we get from experiment, and this is something that we do not expect at all from classical mechanics. So this is another strike which tells us that okay, maybe something is wrong. So either we are doing the experiment wrong, or classical mechanics is wrong. Something is going on. Okay, now is there any questions till this point? Okay, so now moving on to another case, which we will call case 3 here. Uh, so let's have this. Let's just copy this part. So we saw that from the experiment, both up X and down X are coming out. Now we feed, say, let's say we stop this and we extend this. We feed this to another Stern-Gerlach apparatus, but this time oriented along Z. Okay. So with the if we still consider classical mechanics to be somewhat right, then it is obvious that if gamma z it predicted that neither up or down x will come out, but both came out. So it's obvious that here also both uh, up z and down z will come out. This is like according to experiment, and that's what we got all. So, yeah, so of course, in this example also we saw that our classical intuition or the classical sense of a vector did not help us much. But this example illustrates something even more fundamental, as uh, in the first case, what did we have? We had two Stern-Gerlach apparatus, both oriented in the same direction. And we saw that after the first Stern-Gerlach, we had just upset, and then we put another Stern-Gerlach apparatus. Then we didn't get any downset, only the upset we obtained in the at the output of the second Stern-Gerlach. Now, if we compare case 1 and case 3, what we have done is just we have introduced another Stern-Gerlach in x direction, which is perpendicular to z direction. So classically speaking, if we do something in an orthogonal direction, in a normal direction, then it should not affect my outcome. So previously only upz was coming out. Now only upz should have come out. But what we see is that even even though we have put the Stern-Gerlach in an in a perpendicular direction, the output is changed. So the orthogonal directions, in some sense, which we consider to be independent, they are not. This don't seem to be so much independent after all. Like at least according to this experiment. So is that okay? Is that okay with everybody, or like do you get what I'm trying to say? Like if there is any confusion, please let me know.
Yeah, it's fine. It's fine.
Okay, okay. Yeah, okay. So these experimental results motivate us to find some. So it basically tells us that classical mechanics in these contexts, it's not that classical mechanics is incorrect, classical mechanics is correct for most of our day-to-day activities. Newtonian mechanics holds true. But when we are looking at these silver atoms in this experiment, classical mechanics can no longer explain the result. So we need to go to some other theory, and now we know that theory is quantum mechanics. So what we will do next is we will try to uh, uh, slowly lay down the postulates of quantum mechanics. So basically the basic rules which we will assume that they are true, and we will try, and assuming those rules we will try to see whether we can explain this experiment. So let's start with that. Now, the first thing that I would, before going into the postulates, I would like to mention is that is what, how do we do things in classical mechanics? Let's review once. Maybe. So in classical mechanics, if you have a, say, if you, let's say you have a one dimension, in one dimension, a particle is moving. Then how do you describe the state of this particle? So it's constrained to move along one direction. It cannot go, say, if it is along X, it cannot go to Y. So how do you describe the state of this particle?
With its position and velocity.
Yes, position and velocity, or position and momentum, equivalently, because momentum
Yes,
is just, yeah,
momentum.
mass times velocity.
Yes, sir.
So yeah, yeah. So basically, yeah. So these two, if you just mention the position and momentum of the particle, that tells you the state of the particle. And what is this? Like, why am I saying that it's the state of the particle? Because this is everything that I have to know about the particle. So if I know xp, and if I know, say, the total energy of the particle, let's denote it by h, say, which is t plus v. V is kinetic and v is potential energy. So if you know the total, so basically, if you know the potential, because the kinetic energy is again dependent on this. So if you know the potential in which the particle is moving, and we assume that the total energy always remains same, as in we do not consider a dissipative system. We consider that the total energy is conserved, a non-closed system, if you like. Then if I know xp at any point of time, I can find out xp, what its position and momentum, or position and velocity will be at some other, at some later point of time. So it's in one dimension you can say that, so at this point you can uh, specify on this two-dimensional plane. So this xpx plane is known as the phase space, and the state of the particle is just a point in the phase space. And with time, the evolution of the particle is traced in this phase space only. Now, if you can I write a phase space in quantum mechanics? Uh, can I do this for quantum mechanics?
There'll be an uncertainty.
Precisely, yeah. So basically, if we want to specify the position accurately, then we can't specify the momentum at all, like the so because we have the uncertainty relation in quantum mechanics, which gives me this. So if delta px is sorry, delta x is 0, then in order to keep this product finite, delta px has to tend to infinity. In other words, if delta x tends to 0, then delta px has to be infinite, which means that I in this so if I specify this in this direction, it would be infinitely, like it can be anywhere on this line of constant x. So, okay, let me draw this properly. Okay. Huh. So let's say specify the x here, then in px it can be anywhere, right? So phase space picture, because of Heisenberg's uncertainty relations, phase space picture or this kind of a treatment does not really work in quantum mechanics. So now the question arises that in quantum mechanics, how would we treat uh, okay, yeah. Hmm. How would we describe the state of a system? And it turns out that the answer is somewhat non-trivial. So you describe some vector in some abstract space, vector space. So so it's the state of a system in quantum mechanics is described by a vector in an abstract vector space. Okay. Now, what is an abstract vector space? So that's the most obvious question. So instead of answering that directly, I would try to motivate the answer first. So let's say we take the simplest vector space. So the simplest vector space would be our real space. Like if we just take this um, x, y, z. So it's the real space, the space around us, which we can represent by any vector in. So any vector here would look like somewhat like, say, v1 would look like x1 x hat plus y1 y hat plus z1 z. So this is the simplest vector space that you can have. And yeah, and you can also represent it by the ordered triplet x1 y1 z1, and this space is said to be R3. Why R3? Because it's an ordered triplet of three real numbers. X1 is a real number, y1 is a real number, and z1 is a real number. So this is a vector which belongs to this space R3. Now let's consider another vector in this same space. So let's say x2 x hat plus y2 y hat plus z2 z hat. So again, this would be another x2 y2 z2, something like that. Now, how would you define? So in this space, we can define a dot product. So the dot product we define as something like v1 v2 dot v2. This becomes just the product of the corresponding components. So something like this. Okay. Now Another, so this is the uh, dot product in this space. Um, Another thing that we can do, given v1 given two vectors v1 and v2, is that we can take the linear combination. So what does that mean? That means you take the vectors v1, v2, you multiply v1 by some number, say alpha, and v2 by some number, say beta. See, alpha, beta can be anything, say 2, 3, 4, 5, any real number. In this case, any real number. And so if you take this linear, so this is called, doing this is called taking a linear combination. And if you take a linear combination where alpha, beta are real, then you would have something like alpha x1 plus beta x2. Oh, sorry. Is this clear? So if x1 and x2 are real numbers, alpha and beta are real numbers, then alpha x1 plus beta x2 is again a real number. If y1, y2 are real numbers, alpha, beta, so like that. So all these three are again real numbers. So they are again part of the vector space, or let's say space R3. Okay. Now, okay. So till now, is there any question?
No, sir.
Okay. By the way, you don't need to call me sir. Yeah, I'm maybe 1 or 2 years older than you. So now one thing that okay, we have so this is the simplest space which contains vectors. Let's say now what we would like to do is we would like to represent it in a little different form. Like we were using this unit vector notation or the ordered triplet notation. Instead of this, what we will like to do is represent these vectors as vectors as column matrices. So for example, v1 would be written somewhat like x1, y1, z1, and uh, and instead of v1 vector, we would use this notation. So this we would call a kit, and I'll explain why it is called a kit in some time. So let's call it, so this would be kit v1, for example. So kit v1 is x1, y1, z1. So notice that it's the same thing. So instead of v1 vector, I'm just using a different notation, if you will. And so x1, y1, z. Now here we will uh, denote the unit vectors also by kits. For example, x hat, now we will just denote by x, and that would be like 1, 0, 0. Y would be like 0, 1, 0, and Z would be like 0, 0. And with this definition, you can uh, see that we can recover this expression. So basically, you can break this matrix as x1, 1, 0, 0 plus y1, 0, 1, 0 plus z1, 0, 0. And so as we had defined, x1 x plus y1 y plus z1 z. Okay. Now, uh, why are we going into this kind of a very strange notation? simple answer is that it would later on make life easier for us. And the reason we have called it kit, because for every kit vector there is a bra. So for every kit v1 x1 y1 z1, we can define a bra v1. So basically you call this bra. So basically it's just horizontally flipped by 180 degrees. So bra v1 would be uh, the transpose of v1. So this was a column vector. So if you take the transpose of a column vector, it would become a row vector. Now, how would under this notation, how would I define the dot product? Like it used to be the dot product between say v2 and v1 used to be v2 dot v1. Like the notation used to be like this. How do I write this notation? So what we do is that um, so the dot product, what did it give me? It gave me a number. Now I need to combine my bras and kits in such a way that it gives me a number. So now instead of doing a dot product like this, I would just write bra v2 kit v1. So notice bra v2 would be this row matrix. So this is bra v1. So v2 would be it's the same thing with the index being 2. So like this. And kit v1 as we had described will be like that. Now this is a 1 by 3 matrix and this is a 3 by 1 matrix. So if you multiply a 1 by 3 matrix by a 3 by 1 matrix, what you would get is a 1 by 1 matrix. A 1 by 1 matrix means it has only one element, so basically it's a number. So x2 x1 plus y2 y1 z2 z1. Okay, so uh, so basically we can get rid of the matrix notation here and just write it as a number that it is, because 1 by 1 matrix is just a number. So this is just a new notation that we are introducing for dot product. Just for the time being, it's just a dot product, just with a new notation. Till now, any questions?
Yes. Hello.
Yeah, go ahead.
Here we use the three bases x cap, y cap, and z cap, and also vector space has many bases.
Can you repeat your question? It was not very clear.
Yes, vector space is made of bases. Is x cap, y cap,
Yeah.
and also is a possibility that vector space too many bases.
Oh, bases. Yeah. So, of course, you can have like there are infinitely many bases in this vector space. So, as in what he's trying to say is that why do I fix x, y, z? I can take any three mutually perpendicular axes and I would still get something like this. And yeah, you are absolutely right. Yeah, we have just taken this, like you can go to any other basis and you can work there in the same way. So that is completely fine.
Yes.
So for example, you can take a basis like this, which is say tilted a little bit. So that is also a basis. So you rotate about y root and you get a new basis. So you can describe your vectors in terms of basis also. Is that okay?
Yes, yes.
Okay. Okay. Any other questions? Okay. Now, another thing I would like to mention is that let's say I wanted to in this so I have some vector v vector and I want to find its component along some direction n row, and let's call it Vn. What I would do is generally take v vector dot n row, right? So in order to find the component along n. So by my new notation, I can also write this as nv. Is that okay? Where I define. Acha, another thing is that now generally I in here you would typically define the length of a vector, and that you would say ki magnitude of v1, and that would be some root over of x1 square plus y1 square plus z, something like that. So basically you can also write this as in terms of the dot product. So v1 dot v1. So basically v1 dot v1 would give you this, and you take the uh, square root of that. So now in this new notation, since we will instead of just one line, we will put two lines for n. So I'm just trying to say that it's a unit vector, and putting two dashed lines actually means the norm. So norm is the length only or the magnitude only, but it is as we shall say that it is more general than a length or a distance in the 3D real space which we are looking at, right? Okay. Uh, now, now that we have more or less established some form of notation, modified notation, which would help us in learning quantum mechanics. Now let us go on to more general vector spaces. So this was the simplest vector space. So it was the R3 space. Now I can go to a space which is R4. So in R3 you have column vectors which are like x1, y1, z1. I can define a space R4 where it would look exactly the same, just I would add another. So it's kind of a, think of it as a generalization of the real space that we had. But now R4, you can't visualize like previously if I told you a point x1, y1, z1, and I told you an origin, then that okay, this corner of the room is the origin, x1, y1, z1 is so many meters and so on. You could have went to that point and said, okay, this is your point. But now in R4, this is different from our real space. It is again a space. So this x1, y1, z1, w1, this column matrix is again a vector. Just like x1, y1, z1 column matrix was a vector, but this vector you cannot visualize, or rather, I would say you cannot physically point out this vector to me. But this is some abstract vector. It's a generalized form of the real space vector. Is that all right? Is there any problem with that generalization?
Not very clear.
Okay, okay. So and you would define everything in the exact same fashion, like the dot product, the way you define the dot product, like bra v2 ket v1. So by the way, I forgot to tell you that that's the reason why we say bra and ket, because when you put them together in the dot product, they become bracket basically. So the these being the brackets. So you would define your dot product in the exact same way. So just instead of x to x1 plus y to y1 plus z to z1, there will be x to x1 plus y to y1 plus z to z1 plus w to w1. So everything else remains almost the same. So in this way, you can define more general spaces, in general, some Rn space. Now, uh, what if I, instead of taking real numbers, I can also take complex numbers. I can say C3, I can say C4, or let's say I take the simplest case, C2. So C2 would be some, uh, so again, a column matrix like this, only here, what did we have? Here, x1, y1, z1, these were real numbers. Now we will define C1, this column vector C1 and C2, where C1 and C2 would be complex numbers. Now, this would also be this is also another abstract space. This is a vector is in another abstract space, which you cannot really, as I said, physically point out. So, because here you see that C1 I can write as some x1 plus iy1 and x2 plus iy2. So basically there are four real numbers which are describing this, and anything which is beyond three real numbers we cannot represent any longer in our space. So in general, like it seems, at least it seems right now, okay, uh, this is something which is kind of hard to visualize, or it does not have a physical representation as such. Uh, Now, so you could have C2, C3 like that. Now, what about the dot product? Let's look at the dot product. What how would the dot product look like in this space? So let's say that this we have two vectors, say C1, C2, and D1, D2. Okay, so we want to take the dot product, so we have to take the bra of one. So bra of get D would just be the transpose. This would become D1, D2, and if you calculate the dot product, it would be D1, D2, C1, C2, and something like D1, C1 plus D2, C2. Okay. So yeah, now remember how we described the magnitude of a vector in our real space? It was like v1 dot v. So basically it was like root over of v1 v1. And what we would like to do is that we would like to describe the length or the norm, as I said, the generalized version of a length. We would like to describe it in the same. So for example, if I try to find the norm of D, basically a measure of the length of D, then what I would do is just use so it was v1 dot v1 there, here it will be just dd, something like that. So let's see what we get if we do that. If we do this, you can see that we are so basically DC was D1 C1 plus D2 C2. Now the C1 will be replaced by D1, C2 will be replaced by D2. So D1 squared plus D2 squared. Now, as we said, that D1 and D2 are complex numbers. So let's say D1 is some x1 plus y1 and D2 is like x2 plus y2. Then x1 plus iy1 whole squared plus x2 plus iy2 whole squared. So basically x1 squared plus x2 squared, and here it will be minus y1 squared plus y2 squared, but there will be some imaginary part also, like 2i x1 y1 plus x2 y2. So we see that if we define the dot product like this, our length or norm becomes imaginary. And you would say, okay, this is a abstract space. So in the real space, the length was real. In the complex space, the length is complex. What's the big deal? But we want to generalize our vector space in such a way, our real space to some general vector space in such a way that the norm does not become imaginary. It remains real and it remains positive. So the length in, so for R3, for the real space, for R3, we had the length or the norm was greater than or equal to 0. I want that for C2, the space that we are dealing with right now, the norm should be greater than equal to 0 as well. But we see that by if we define the dot product like this, then we cannot uh, get that. So basically, this definition of dot product is wrong for the C2 space, for this space. We cannot define dot product like this. So instead, what we define is a generalization of dot product, which we call the inner product. And so what did we have? We had C and D like this. Okay, let's just copy. Okay. 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 Hmm. Now, previously, remember what did we do? We defined a bra of D. What we said is that the bra of D would be just the D transpose, and that gave us the column vector D1, D2. Now we define that the bra D should not be just D transpose. In this space, the bra D would be D transpose complex conjugate of that. So basically, you would have D transpose would be D1, D2, and complex conjugate of the whole thing. So what that means is that every element would become complex conjugate as well. D1 star, D2 star. Like a complex conjugate means ki if D1 is like x1 plus I by 1, D1 star would be x1 minus I by 1. So that is what we mean by complex conjugate. Now, with this definition, so CD, or what did we calculate? CD or DC? Okay. DC would become this. That is D1 star C1 plus D2 star C2. Sorry, D2 star C2. Yeah. And what now? What if we try to find out the norm of D? sorry, norm of D, so DD inner product. Now this would be D1 star D1 plus D2 star D2. And D1 star D1 is not nothing but mod D1 squared, and D2 star D2 is nothing but mod D2 squared. And that, my friends, is greater than equal to 0 as we want. So in this space, we had to uh, uh, change the definition of the dot product and call it the inner product. And notice that it's not necessary that for all spaces, the inner product might not look like this. The definition of bra D, which we used here, might not hold for some other vector space. So inner product is more general than the dot product. It does not have a specific definition. It can vary from space to space. And you can define it in your own ways as long as it follows certain rules. And maybe next day we will talk about those rules. Okay, so is so what I have been trying to get at in this with this discussion is that you can generalize, although you can't have a real space which where the elements look like C2, but you can have a generalization of the real space that you have. And basically, if I have to, in very simple words, if I have to define a vector space, so a vector space is just a generalization of the real space, but notice that it can't be any generalization. Some of the flavors, some of the aspects of some of the rules that were followed in the real vector space have to be followed in this space as well. For example, we had this rule that the norm, so basically the norm is also a generalization of length. Because if you think about it, I mean, in the complex C2 space, the length of a vector, you might think, okay, it's hard, you cannot really visualize as the distance between 2 points like that. But the norm of a vector, which is the generalization of this length. So we have this rule that this has to be positive, just like the length used to be positive in the real vector space. There has to be some definition of something like the dot product, which we saw is the inner product. So is generalization of dot product. So is a generalization of the real space, which uh, follow similar, where the vectors follow similar rules. So is this understandable to people? Like I know maybe a lot of you are already familiar with the concept of vector spaces, but for those who were introduced it for the, so is there anybody here who has been introduced to vector spaces for the first time maybe? So all of you knew vector spaces before, right? Okay, 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 okay. Fine. So I guess it was kind of a revision for you. So um, if in case if there was anybody in the audience who did not know about vector spaces, then hopefully it was a it was kind of a good introduction to the topic. So today what I have done is I have introduced vector spaces in a very informal way. Next day, maybe, which will be, I think, this Saturday. So we will let you know about the timings later on. So we will introduce vector spaces in in a more formal fashion, and we will lay down the postulates one by one on Saturday. Um, Okay, so that's all for today. So I'd like to know some feedback from you. So because I have been I have not really taught in a say online mode or to such a large audience before. So am I going too slow, too fast? Any feedback if you guys have, I would really appreciate it. Any negative feedback is also welcome. Where is hmm,
Sir,
hello?
hello.
Huh,
Yes,
all right.
so I have studied these vector space in in my course before, but as you
Uh-huh.
explained it, I could never have grasped it that way. So you explained it fairly transparently. So thank you for that.
Okay. I actually, I'm sorry. I think there's a connection problem. So I didn't hear you well. So, so basically, you're saying that it's better to start from the rules of vector space and explain it like that. That would be better.
No, sir, I was saying that I have read these before, but you
Okay.
explained from the basic way and very elaborately. So I gathered more and more of it
Oh,
from
oh,
you.
oh, I'm so happy that you actually benefited from that. Okay, okay. And actually, next day we will also do in the way normal textbooks would describe it. So I think that way, that time you would also be able to like relate more to the stuff. Okay, thanks, thanks. And any other comments? Any other comments? Anything? Any questions about the experiment? Because these are concepts which are not always so easy to understand. So if you are not understanding anything, if you have any problem, please speak up. Okay, you can also stop me when I'm teaching. You can also stop me and ask me, so there's no problem. Okay. And okay, so I'll maybe wait for 2 minutes and okay.
Excuse me, sir.
Yeah.
Sir, about the Stern-Gerlach experiment.
Okay.
In case when we are um, uh, these silver atoms are added and there's a
Mm-hmm.
magnetic. So
Mm-hmm.
we have two of such apparatus uh, through which through the second apparatus we are only providing the z direction spins of these.
Right.
So in that case, cannot we get two different spins like up z and down z spin?
So you are talking about the case one or case two?
Case one, sir.
Case one. Okay. You are saying ki why can so after the second Stern-Gerlach along Z, why didn't we get another down Z? Is that the question?
Yes, sir.
Okay. So this you can understand with classical mechanics only, right? So when I am saying that here there is a up Z, what I mean is that the SZ is plus h cross by 2. And since so basically if I write the S vector would be what? SZ Z roof. So plus h cross by 2 Z roof. And what the other Stern-Gerlach will see is that it will see only up Z here. So this is the SGZ. This is what is happening inside SGZ, right? So previously what was there is that there was up spin and down spin both. So the out spins went here and the down spins went here. Now I have removed the down spins. So you tell me what will happen. This will not come. No, this branch will not come. Only this will come. Now can you understand it?
Sir, isn't it possible that the magnetic field may flip some of the spins to the downside?
Isn't it possible that the magnetic field can flip? Okay.
Since it's a non-uniform magnetic field, so maybe the spins, upside spins may get flipped down, like to downside. Maybe
Okay,
some.
okay. That is an interesting question. Like in principle, yeah. So what's stopping it from flipping to down Z, for example? Okay. Um, right. So we have this. Okay, let's try to see what is happening. So we have this force acting on the silver atom, and that force is dependent on mu z, so basically on sz, on the spin of the particle. So the force is dependent on the spin. Now let's say when it reaches the portion of the inhomogeneous field, say let's say like what you are saying is true. Let's assume that to be true, that okay, it was a upspin here. So it initially will start experiencing a force here in this direction, and then suppose in in between somewhere it changed to downspin. Then what will happen is that it will uh, again, so because if it changes to downspin, mu z will now become negative, and then it will come somewhat like this. It will follow some trajectory like this. So I don't know, like I have to do the maths. I don't know, like I'm not doing the maths rigorously, but if you think about it, if the particle is experiencing a force continuously like this, like from here to here, it was the same mu z, no flipping involved. It will reach some spot. Now, in between, if it flipped, then I think like if the force starts acting here, then the trajectory would be different and it would hit some other spot. Isn't is that right? Because the force in the negative z direction starts acting at this point and not at this point, as with this set of particles. Is that clear? Is that
There.
hello?
Hello.
Hmm.
Yes, sir. I understand that.
So basically, you would if that had happened, like if it had flipped in between, then what you would see is that you would see a spot, but that would be different from the spot of the down z particle. So basically, if say in the initial so consider the initial situation when both up z and down z were there. In that situation, you would actually get different spots here. And so if that had happened, but we don't get that, right? We only get two spots. And suppose if you say ki after escaping the field, then by your logic, if the non-uniform magnetic field is causing the flip, then after escaping the magnetic field, then there should be no flip. So whatever flip should happen in this region, and in that case you would get a series of patches like this. But in experiment you don't get that. So I think from that we can argue that that process is probably not happening, or is definitely not happening. So with this, basically we can prove by contradiction kind of thing. Is that okay?
Right. Right. Thank you, sir.
Okay. Okay, I'll wait here for maybe 5-10 more minutes. Any questions, just let me.
So, participants, do you have some other question?
Sir, sir, could I ask one question?
Sure. Go ahead. Yeah.
Actually, in the Stern-Gerlach experiment, the neutral argon atom and the last outermost electron is in monopole, right?
Come again.
The outermost electron of the atom, argon atom, neutral, that is a monopole, 5s1, one electron.
Monopole. No, see, 5s1 means what? If you look at the say, so this is the 5s orbital, for example. So there's only one electron, no? So if there's one electron, then it's an unpaired electron. Unpaired electron will always have a dipole moment, which is so okay. So basically, this dipole moment that it has is related to the spin angular momentum.
Yes, sir. Yes.
Okay, so it won't have like a monopole, as in ki the orbital angular momentum is 0, but the spin angular momentum is not 0, right? So it will have a dipole moment. It will not be a monopole, right?
Yes, sir.
So basically, again, that brings us to that relation. Ki how is the magnetic moment related to the angular momentum? So it's just related by a factor gamma. So if Sz is not 0, mu z will not be 0, and you will have a dipole moment.
Okay, sir. Okay.
Okay.
Yes.
So, Anuvab, do you wait or?
Yeah, maybe I'll wait for a couple of more minutes in case they have some other questions. Couple more minutes, and then maybe I'll leave. So is there anything else which is scheduled now? Hello.
Sir, next tutorial session, according to the mentioned in the program schedule, right?
Next tutorial session, according to the program schedule, will be on next Wednesday, but we will have a we will probably have a tutorial before that, tentatively this Saturday. So we will let you know the timing. So we don't know exactly when it would happen. So let's see. Okay.
Yes, sir.
We will let you know by email.
Yes.
Okay.
Okay, sir. Okay.
Huh, huh.
Hello.
Hello.
So participants, you
Hello.
can ask a question if you have. So Anuvab is here waiting for your question. Our next session will start at 5:30. So please don't leave.